All right, well, hello everyone. My name is Garrett Karto Keating, and I am the SMA project scientist. And right now I'm going to talk to you, basically give you an overview and introduction to interferometry, and try to introduce you to some of the basics about how it works. And hopefully by the end of this talk, you'll have at least some physical intuition as to what exactly it is that we're doing with these radio telescopes and what are the quantities that we're trying to measure. And then kind of future talks will build on how we use that information to make maps and other measurements of the sky. So before I dive into it, I usually like to kind of review a little bit of the math that I'm going to be using throughout the talk. So in this talk, I'm going to be talking a bit about convolution, cross-correlation, and autocorrelations. And these are all kind of interrelated concepts, but the idea is with all three of these things, you have two different functions, and typically you're sliding one function against another function and kind of taking the sum of all the different points at each kind of step. So in a convolution, I've got a square and a triangle wave kind of sliding past each other, taking the sum at each interval. And in a convolution, it doesn't matter the order. F convolved with G is the same as G convolved with F. In a cross-correlation, typically the second of the two functions is flipped, or one might say conjugated, so the order actually does matter, and so G convolved with F looks like the mirror image of F convolved with G. An autocorrelation is basically just a correlation with the function by itself, so these typically look very symmetric. But otherwise look very similar to what you would expect with a cross-correlation with two identical functions. So, why is this of interest? Well, kind of comes down to this, which is the Fourier transform. Fourier transform you can think of as a correlation or a convolution of some function times this weird exponential thing that's over here that looks kind of like gobbledygook. But thanks to Euler's formula, you can actually write this out as a series of sines and cosines. And in fact, Fourier transform is used for transforming things that look like sine and cosine waves in one domain into effectively delta functions in the other domain. So radio astronomy is very, very heavily indebted to the existence of the Fourier transform. It powers a lot of what we do. In fact, you might hear talks about a fast Fourier transform and FFT, and all that is basically just a fast algorithmic way of executing a Fourier transform under very particular circumstances. So, one thing that I will kind of allude to during the talk is this idea of the convolution theorem, which basically says that the Fourier transform of one function convolved with another function is equal to the Fourier transform of the first function times the Fourier transform of the second function. Seems like a very simple rule, but actually this turns out to be a very powerful thing for radio astronomy, for reasons I'll get to a little bit later on in the lecture. So, diving straight into it, what is an interferometer? Well, like most things in radio astronomy, it starts with an antenna. And in fact, for an interferometer to exist, you need at least two of these guys. So two antennas together we typically call a baseline. So imagine that there's two antennas sitting out in a field somewhere, and somewhere way off in the distance is a monochromatic, so broadcasting only at a single frequency or a single wavelength, stationary source that is infinitely far away. From this source is broadcasting radio waves, and you can imagine these radio waves kind of coming down like almost like sheets of rain in these kind of planar waves. So the idea being that, if you were to measure the electric field over here versus the electric field over here, kind of it's moving in lockstep with one another. These planar waves are basically traveling all together. So it doesn't kind of matter where you are across this imaginary plane here. And they come to the antennas, these radio photons come to the antennas, they get collected, you put them onto cables, and these cables bring the radio photons to a correlator, or it can even be a simple analog device called a mixer, which in fact many of you may have, without knowing it, used before in things like car radio or cell phones. It's a very common analog component. And out of this mixer, out of this correlator, comes the interferometer response. And it's the interferometer response that we're particularly interested in. So, What does this all mean? Well, kind of diving more into the details of what this interferometer response is. At each antenna, what's happening is it's converting radio photons coming into the sky as a fluctuation of voltage basically on a cable. And so I can actually write out a description of what the voltage looks like kind of at the antenna at a given time. And so I have light coming in at a very specific frequency, so I can actually write out, what the voltage looks like, basically as a cosine function over here. You'll notice actually that the voltage measured in antenna A and antenna B are close, but they're not identical. There's this little plus delta part that's here. The origin of this delta comes from the fact that when the light is coming in this plane wave, it actually has to travel this little extra distance, this red distance that's right here, in order to reach the antenna B. And that little extra distance is basically the source of this delta. So you can actually calculate what this distance is. All you need to know is the baseline vector, the unprojected baseline vector, so the physical distance between the two antennas, and the elevation angle to the source. And you can actually calculate what the path length delay is for the photons basically traveling along this path. So that's the source of this delta. The voltages are transmitted down the line to the mixer, and the mixer, from a mathematical perspective, is actually very simple. The only thing that the mixer does is basically multiply voltages together. So in fact, you can do the math, if you remember way back to your trig classes in high school, you can actually write out the expression for what the voltage looks like coming out of the mixer. And if you do all the math, you come up with two components. So there's this one component that's a time-varying component, hence the little t that's there, that's actually at twice the frequency that was measured on sky. And then there's this other component that does not have a time-varying component, which only depends on the frequency that you're looking at and this geometric path delay component. So, and in fact, as with many things in astronomy, we do typically average over some amount of time. And so when you do so, you actually end up with an output voltage coming from the mixer that only depends on this geometric path delay. So what this is telling you is you can say something about you can either think of it as being the elevation angle or the position of the source by measuring the voltage output coming from this mixer. I think that's pretty cool, actually, that you can you can ascribe a position of something in the sky based on the voltage coming from an electronic device. So, but that's the basic interferometer response. So we have this nice expression for what the voltage looks like coming from the mixer. Let's kind of play around with this a little bit further. So if we have a source that's directly overhead, where the elevation is 90 degrees, cosine of 90 degrees is 0, anything times 0 is 0, and of course cosine of 0 turns out to be 1, or at least a positive number. And so we would measure a positive voltage coming out of the mixer from this position. You can imagine that there's another position where this equation basically ends up, the terms inside here end up canceling out, or basically forming 2 pi. And so the cosine of, sorry, not 2 pi, but pi over 2. And so the terms inside here basically cancel, and you get voltage that's roughly equal to 0. And finally, you can imagine another value, say pi in this instance, where or some multiple, some odd multiple of pi, where you get out a negative voltage. Depending on where in the sky you are, you will get a positive or negative voltage. So you can imagine if I actually made a plot of what the voltage looks like as a position of elevation angle or as a position on the sky, I would get out this plot. Sometimes you will hear radio astronomers refer to fringes or fringe patterns. This is what they're talking about. They're basically talking about this cosine pattern in the sky. And in fact, if a source was moving, like astronomical sources typically do across the sky, you could actually make a plot of, instead of position angle in the sky, kind of voltage versus time coming out of this mixer output, and see this modulating voltage go up and down and up and down. So that's great. You might notice that we only talked about the cosine component, maybe wonder yourself, well, what happened to the sine? And in fact, there is a way to tease out the sign information, or the so-called asymmetric piece of the information of the sky. And the way of doing that is that you just introduce a little bit of delay, a little thing that basically phase shifts the signal by 90 degrees. So instead of getting a cosine pattern in the sky, you get a sine pattern in the sky, such that at directly overhead, you get 0 voltage, and then you get basically a pattern that's shifted by 90 degrees. These two patterns actually contain different pieces of information. They're orthogonal functions in the sky, so they are orthogonal, or different pieces of information that you can measure. And they are telling you, again, something about the position in the sky of a given source. So typically, when we talk about these two different mixers, or these two different correlators, sometimes people talk about real correlators, which is the cosine pattern component, and then the so-called imaginary correlator, or the sine component. Real and imaginary, though, keep in mind, these are just kind of mathematical conventions. There is no such thing as imaginary photons, or if there is imaginary photons, they don't actually exist, and they don't actually enter the antennas. Everything, the photons are real. The mathematical conventions are the things that are imaginary. So just keep that in mind. All right, so that's the interferometer response. That's the fringe pattern in the sky. Let's look at this equation a little bit further and see maybe how we can play with this and maybe learn kind of more information about what's up in the sky. So looking at the terms that are inside here, you might notice right up front there's this D term. This is the physical separation of the antennas. We can change the fringe pattern by changing the distance between two antennas. In fact, I can make a higher frequency fringe pattern by moving two antennas apart. And likewise, I can actually make a lower frequency fringe pattern on the sky by pushing antennas together. And in fact, this is kind of the core of aperture synthesis, is this idea that you can actually have multiple baselines of multiple different lengths, each measuring a different sine or cosine pattern of the sky. And it turns out that if you measure all of the sine and all of the cosine patterns in the sky, you can use a Fourier transform and reconstruct exactly, with enough information, what the sky looks like. So that's really the big power of interferometry, is to basically reconstruct images by measuring different fringe patterns in the sky, measuring the emission in those fringe patterns. Important thing to keep in mind here is that the resolution of the interferometer is basically set by the baseline distance. So if you want to go very high resolution, you can move your telescopes out very far apart. And if you want lower resolution, in order to capture a kind of larger scale structure, you can push your antennas all together. In fact, this is part of the reason why SMA, at least, has multiple configurations that it can go to, because different people have different science interests that require different resolution. And you can accomplish that by moving the individual antennas of the interferometer out or in. So you can change baseline distances to get different fringe patterns. What else can we change? Well, we started talking about this as a monochromatic source, but imagine instead that, in fact, when we look at sources, they can emit at multiple frequencies, say like a continuum source, which emits at lots and lots of different frequencies. There is a frequency component, a sky frequency component in this fringe pattern. And in fact, you can get larger mode or smaller mode fringe patterns in the sky by changing the wavelength of the light that you're looking at. So you can see that the shortest wavelength has the kind of fastest moving fringe pattern, whereas the longest wavelengths, the red here, has the very slowest moving fringe pattern. Now, you might notice something a little weird here, in that, right here in the center, right at zenith, everything looks nice and coherent. So that's nice, that's good. You can definitely detect something there. But you might notice that there are certain positions here where you actually have different wavelengths producing kind of interference patterns. And in fact, you can have different wavelength voltages basically canceling each other out. On top of this, radio telescopes typically don't see the entire sky. There are special telescopes that can see a good fraction of the sky, but usually you are limited to seeing a much smaller sliver of the sky. And we talk about the field of view of the telescope as being the primary beam width, or the full width half max. For the SMA antennas, that's about an arc minute across. So definitely much smaller than the field of view across the sky than the whole sky itself. So this, of course, is a problem because even though there might be a source in here, if I'm sensitive to multiple different frequencies, those different frequencies might produce kind of interfering fringe patterns and may cancel out and result in kind of a nulled out emission, and I might not detect anything out of this mixer. So what do we do? Well, typically what's done is the reason for this is that, of course, different wavelengths of light have basically have different fringe patterns across the sky, and they only line up when the telescopes are basically kind of exactly coplanar to the sky, and that is where the geometric delay towards the source is 0. So we actually use that to our advantage and put into the system something that can compensate for this delay, basically add an extra delay component to compensate for the geometric delay going towards a particular direction of the sky. So rather than seeing this kind of incoherent mess, we actually see all the fringe patterns line up. So this is actually what's typically done for most radio observatories. It's called fringe rotation or fringe stopping. Basically, it's making it so that all the fringe patterns line up in the center of the field of view. And in fact, it's not just at one particular view at one point in time, but typically when the telescope, say, moves over to another position, we change fringe tracking so that the center of the field of view, you're always looking, you always have the fringe pattern set up so that they're kind of maximally coherent in the center of the field of view. So you kind of eliminate this incoherence problem. So that's nice that we can kind of play around with delays to at least make things coherent. But there is, in fact, another thing that we can do with delays, which is you might notice that because these different fringe patterns, these different frequencies have different fringe patterns, they are jogged back and forth by kind of relatively different amounts in kind of degrees or cycles by differing amounts of delay. And so what you can actually do is, rather than measuring just the output of the mixer where the signal is delayed just once or has only one delay in it, you can actually introduce, say, a box that out of it comes signals with multiple different delays and actually measure from different correlators or different mixers the output voltage from each one of these different mixing products. So what does that look like? Well, it looks a little bit like this, this thing that we sometimes call a lag spectrum, where right here I'm basically plotting the voltage response as a function of this little added delay, this tau sub s. So this looks, kind of neat, but what is it really good for? Well, through, again, the magic that is the Fourier transform, you can get out a frequency spectrum. That is, you can actually measure the interferometer response as a function of frequency by using the Fourier transform and the lag spectrum. So this is actually typically how one does spectroscopy with the radio interferometer. Some things to kind of keep in mind here. So we typically, this kind of set of data points or this set block of frequencies, the whole block we sometimes call a spectral window. At SMA we also call it a chunk. We used to call them quadrants when we had 4 of these windows altogether. Now we've actually got 6 chunks, so we sometimes call them hextants, sometimes call them segments or blocks. Lots of different names for basically the set of all these different frequency, the whole frequency block. The individual points we typically call a channel. So we have lots and lots of frequency channels inside of a spectral window. Some things to keep in mind here. So both the width of the spectral window and the channel width are set by things that are in the lag spectrum itself. And so the channel width is actually defined by the kind of total sampling delay time, or if you have some sample interval tau sub s, your channel width is defined by 1 over the number of different delays that you sampled times that tau sub s. And similarly, the full bandwidth window is actually set by the increment in individual delay components. In fact, it ends up actually being 2 different values depending on whether or not you've got complex or real-only sampling due to kind of Nyquist criterion limits. I won't go too deeply into that, but needless to say, the kind of finest scale on the lag spectrum sets the largest scale on how big the spectral window is. And in fact, the total length of, or the total set of delays, that total width and time, actually sets how narrow the frequency channels are. So, one more thing to kind of take away from this big picture. Thanks to the convolution theorem, so we typically call, when you correlate first and Fourier transform next, you typically call that an XF correlator. You can actually flip the script and Fourier transform first, so you have this channelized data, and then actually cross-correlate the channelized data to output the same thing. There are some subtle differences. This is called an FX correlator, and there are some subtle differences between that and an XF correlator, but for most intents and purposes, they're basically producing the same exact thing thanks to the convolution theorem. ALMA, for example, has an XF correlator. SMA has an FX correlator. I'm going to continue working with the XF correlator example, but just know that kind of both of these things are doing very similar things, and you can kind of sort of treat them mostly the same. So, after the data comes out of the Fourier transform block, each channel kind of you can write, or each frequency channel you can write out this equation for what's coming out. So we've got this long equation, R is equal to GA GB times this curly V plus epsilon. All right, what does this all mean? Well, let's break it down a little bit here. So R is just the interferometer response of the baseline between antennas A and B, is equal to G sub A and G sub B are actually the instrumental kind of factors. Basically, they are the instrument itself kind of imparts a phase and amplitude characteristic on the incoming photons. In fact, it's something that we have to account for, which in fact I believe Mark is going to talk about in the next lecture. And so, but you have to keep in mind that basically the instrument imparts its own response onto the incoming radio waves. Times this curly V is what we sometimes call the true visibility of the baseline. That is it's the Fourier transform of the sky given some position U and V, where U is kind of the separation of two antennas in the horizontal direction, and V is the separation in the kind of north-south direction. Plus epsilon. Epsilon is the noise of the interferometer, which we'll talk about in just a minute. So the nice thing about this equation, or I should say the very powerful thing about this equation, from each one of these antennas we could be processing billions of data points per second. The SMA ingests tens of gigahertz of data per antenna. And so you can imagine that coming out of this Fourier transform block are billions of data points per baseline. It's a lot of data to have. Fortunately, most of this stuff actually stays relatively stable with time, and it's just the noise that fluctuates around. So in fact, what we typically do is sum or average data over some period of time. Typically it's on the order of seconds, sometimes up to a minute. But that greatly averages down the data that we have to record on disk by factors of thousands. And so rather than getting petabytes of worth of data, you can get gigabytes worth of data. And this is the thing that's actually stored, is the kind of the accumulated sum after some integration time is typically what we call it. And we can only do that because all of these components, save for the noise, which should be random, should be stable at least over that interval of time. So this is great, this is exciting, but we should talk a little bit more about what this epsilon is, because of course the noise is the thing that's dictating how much science we can do, or how deeply we can dive into the interferometer response. So before diving into the noise of the interferometer, let's talk about the noise that comes actually from a single telescope, which is actually typically described by this thing called the radiometer equation. And we have this equation for what that describes. Sigma t is equal to t sub s plus t sub a, all divided by square root of delta nu times tau. So, of course, these things all have definitions. Delta nu is the bandwidth of the radio detector, tau is the integration time, and then there's these two other components, the system temperature and the antenna temperature, which are a little bit weird, but you can kind of think of them as follows. So if you imagine the sky as having a particular brightness temperature, what the antenna temperature is basically it's the brightness temperature averaged over the field of view of the telescope. So that's what the antenna temperature is actually measuring. The system temperature, which is a slightly weirder concept, but it's basically, you can imagine that if you had a perfect antenna, a perfect receiver with zero noise, and instead had a block of absorber at some temperature. So let's say we had a system temperature of 40 Kelvin. Instead of you had a perfect antenna and just a block of absorber at 40 Kelvin. What you would measure with the antenna would be basically identical to what you would measure with just the system noise coming from the telescope itself. So the system temperature is basically a way of describing the noise of the instrument using brightness temperature units. And in fact, the way that we actually typically measure it is we do what's sometimes called a Y factor measurement, which is we measure the power coming from the system first before putting anything in there, and then we actually put in a perfect, or hopefully close to perfect absorber. And of course, by Kirchhoff's law, perfect or good absorber is also a good emitter of light. We know the temperature of the absorber, hopefully it's at ambient temperature, and we can actually back out what the system temperature is by introducing a load of known temperature. So this is how we get system temperature information. Once we have that, once we know what the system temperature is, then we can actually describe what the sensitivity of the interferometer is, which is this new equation, which again might look a little scary, but again, defining terms here. So the RMS noise in units of flux density is equal to √2 times Boltzmann constant times the system temperature, or in this case it would actually be the square root of the system temperature of antenna 1 times the system temperature of antenna 2, all divided by the effective area. So that is the geometric area of the dish. So we have a 6-meter telescope. So, pi r squared, we have roughly 18 square-ish meters of collecting area times an efficiency factor. That aperture efficiency can range anywhere from kind of 0.5 all the way up to, I think, hypothetically 0.85. For SMA, it's 0.75. And so all that, again, the effective area multiplied by the square root of delta nu times tau. This gives you basically the noise of the interferometer and what to expect from a single baseline. You can do better than this, of course, because an interferometer has not just one baseline typically, but many baselines. And so usually on the SMA, you can get root 28 times better sensitivity or lower noise because we have 28 baselines, given that we have 8 antennas. There are some caveats to that where that's not 100% true, but they're kind of not worth talking about here right now. So, real quick, so that's kind of what the interferometer is measuring, what's actually coming from the output of our correlator. That's the data that you're actually looking at. Voltage coming from the sky with a little bit of system noise, imparting a little bit of noise voltage of itself, all getting thrown down the pipe through cabling, into a correlator. It's being Fourier transformed and then written to disk for you guys to look at some point. There are some really cool, fantastic advantages to interferometry versus kind of you can think of as our competitor or our counterpoint to interferometry, which is single dish observing. The first of which being that you can actually build very high resolution instruments with an interferometer a lot better or a lot cheaper than you can something with a single dish. In order to get the resolution of a 100-meter baseline with a single dish, you have to build a 100-meter antenna, and that's very difficult to do. And then when you start talking about longer distance, like 500 meters, which is the total distance of the SMA itself, or 12,000 kilometers, which is the diameter of the Earth, which is the largest interferometer in the world, or one of the largest interferometers of the world, I should say, part of the EHT, which we'll talk about later on in school. Very difficult to build a single-dish telescope the size of the Earth. The interferometer has capabilities for reconfiguration typically, so we can move around the antennas and actually get different spatial resolutions, which is great. We can kind of suit the needs of different projects that are of interest. One nice thing about the interferometer is that our noise actually averages down to 0, versus a single dish, you're almost always not averaging down to 0. Those who have worked with single dish data might know about baseband corrections and things like that, but it can be very difficult to suppress kind of noise biases in single dish data, integrating very deeply down. Whereas interferometers, you can spend thousands of hours on the sky hypothetically and still be perfectly fine chugging along. And finally, interferometers natively give you multi-pixel images, whereas a single dish, if you only have a single detector or a single receiver on the telescope, it's a single pixel camera. You can slew that around, of course, and kind of smear out that sensitivity, but at each instance in time, of course, you're only getting a single pixel at a time. So there are some disadvantages to keep in mind, most notably that even though you have a 100-meter baseline, that doesn't mean that you have the full collecting area of a 100-meter dish. So single dishes, big single dishes can be much more sensitive than interferometers because, of course, what matters in terms of sensitivity is just the total collecting area. And so if you've got a bunch of holes in your aperture, in your synthesized aperture, which is what the interferometer has, you don't gain that sensitivity back, whereas single dish, they get the full collecting area all the time. You can't use incoherent detectors like bolometers. Bolometers tend to have lower noise properties than coherent detectors like heterodyne receivers. The reasons for that are kind of beyond this lecture, but typically if you're looking at pure sensitivity limited measurements, you can sometimes do much better with a single dish, particularly with very wide continuum like objects that you're looking at, with certain caveats. Data processing for interferometers tend to be a lot more complex, as you're probably going to learn over the course of the school. And that's true both in terms of real-time processing that has to be done and also offline processing that has to be done. And finally, the largest scales that the interferometer can recover are basically the field of view of the telescope itself. And even that's kind of pushing the limits a little bit. You can typically only get spatial scales smaller than the field of view, whereas in fact, single dish tends to be in the opposite. It's very difficult to get spatial features smaller than the field of view, but easy to get features larger than the field of view. So if you're looking at very big objects like things that are square degrees across, sometimes it's easier to map that with a single dish versus with an interferometer. So hopefully that gives you some insight and some ideas on how interferometers work. This will hopefully kind of build upon further things that will come up in lectures over the course of the next couple of days.